Welcome to FireCAD Water Tube Package Boiler tutorial. In this tutorial, let us design a sample 30 tons per hour natural gas fired steam boiler. These are the boiler parameters. Steam capacity is 30,000 kg per hour. Steam pressure is 45 bar and temperature 450 degrees centigrade. Fuel is natural gas. Water inlet to the boiler is coming at 105 degrees centigrade, and the back-end temperature, that is boiler exhaust gas temperature, is 125 degrees centigrade. In this boiler, let us consider economizer is present as well as an aerator is also present. Once you double click on the water tube package boiler icon, you will get this input form. Let us start filling the input form using the details available with us. Let us select SI units. Steam capacity is 30,000 kg per hour. Steam pressure is 45 bar. Steam temperature is 450 degrees centigrade. And water inlet temperature is 105 degrees. Back-end temperature is 125. Let us select natural gas as fuel. So this is the natural gas fuel composition with methane as high as 90%. If the composition is different, then you can customize these values. You can give your own data here. So the gross calorific value is from database 50,700. Whereas if you see the calculated value is 50,685. Suppose you have a different value, you can give that as input. Let us take the database value, which is 50,750. In the heat recovery section, we can select both economizer and air heater. So select both. The economizer type is bait tube here in this boiler. We can as well go for a finner tube where you can select a fin type. In this case, we'll select only bait tube. Project name you can give as sample. So once the data is fed, you can click run to see the boiler basic design and section-wise details. This is the output from the software. 30,000 steam capacity, 45 bar. These are the summary of the values. You have an efficiency of 84% based on GCV, whereas on NCV it is 93%. Boiler exit gas temperature is coming 127 degrees. Natural gas fuel consumption is coming 2000 kg per hour. Then you have this GCV and NCV values. Then also efficiency breakdown, dry gas losses, moisture in air losses, unburnt losses and all that. Excess air is 10% because this is a gaseous fuel. Unit wet gas, unit wet air. And here you see summary of all the temperatures in each section. So this has got close to 5 sections: furnace, then boiler bank, then superheater, then economizer, and then aerator. So let us do here, customize section by section the complete design of the boiler. In the furnace section, the furnace looks like this, D-type. You have furnace width and height, and this is the furnace depth. And there is boiler bank on the left side, top drum, lower drum connected with boiler bank. So the software has given us approximate dimensions of the furnace. Furnace width is 2200, depth is 7 meters. So these values in the text box can be customized. Suppose instead of 2200, if you feel you should go for 2500, then you can enter this value, press redesign, and see the changed parameters here. Because you increase the furnace depth, furnace volume increased from 52 to 59. And because of bigger volume, the furnace outlet gas temperature came down to 1130 degrees. The gas flow rate remains more or less same. This is volumetric release rates. This is nothing but heat released per meter cube of volume of the furnace. This is a very important parameter here. If you see this section, furnace has got 4 walls. Front wall, no tubes, means it's a refractory wall where the burner sits. You can change this. If you have a different type of configuration, you can select a membrane wall here if the front wall is membrane wall. And side wall here, the software is saying membrane wall. Rear wall is a space wall. Division wall is a tangent wall. You can change these values based on your requirement. Now, coming to, see here, if you see the furnace exit gas temperature is 1129 degrees. This gas at 1129 now enters the boiler bank at the aperture section. This is the boiler bank, how this looks. Top drum, lower drum connected with the boiler bank. If you see the top view, gas from furnace is entering at this aperture into the boiler bank. So after the aperture or screen, you have a superheater here located. Then there is boiler bank at the downstream. Now as far as boiler bank is concerned, here the number of rows are 50. Rows deep is 50. 10, these are the tube wide, and this is 10. And transverse pitch is 120 here, and longitudinal pitch is 89 here. Then there is boiler bank width, and there is boiler bank depth. So if you see the temperature profile of this section, gas is entering at 1129 degrees at the aperture, and the gas temperature falls down to 1043 at the outlet of the aperture, means at superheater inlet the gas temperature is 1043. Now the boiler bank is after the superheater. Gas temperature is 709 degrees, gas outlet is 543 degrees centigrade. This is outlet of the boiler bank. Then you have steam temperature, because this is a boiler bank. Saturation temperature at 45 bar is around 260 degrees centigrade. This is the draft loss. This is the heating surface area. Gas mass velocity is usually kept at 20,000 in such cases, 20,000 kg per hour per meter square. This is overall heat transfer coefficient. If you want to change these values in the test box, you can change. Suppose instead of 50 rows deep, the boiler bank is 60 rows deep. Here I changed 50 to 60. Then press redesign. See, the outlet gas temperature came down from 350 to 328 degrees centigrade. So let's go back to 50 degrees centigrade. It's very important that if you are changing the number of rows deep here, you also take care of the depth of the boiler bank. Software doesn't do it automatically. You have to do it manually. So if you are putting here 60 deep, then 60 into longitudinal pitch, which is 90, that plus superheater depth gives you the total depth of the boiler bank here. Okay. So screen outlet here, if you please note this temperature, 1043 degrees centigrade. Now come back to superheater. In superheater, the gas temperature entering is 1040, this one, and gas outlet temperature is 709 degrees centigrade. This outlet temperature, now if you go to boiler bank, from superheater, that 709 degrees centigrade is the inlet to the boiler bank here. This is the furnace outlet temperature. Then the same is screen inlet temperature. Then there is screen outlet temperature, which is same as superheater inlet temperature. Superheater outlet temperature is boiler bank inlet temperature. Please, this one section by one section it comes. So now coming back to superheater, we want to have 450 degrees temperature as superheater outlet. This is an inverted U-type superheater. It is a drainable superheater. It has got in this section number of tubes per section. Here it is 5, and what's software is predicting is also 5. Sometimes it can be 4, sometimes it can be 6 based on the steam velocities. So now the software predicts number of tubes per section should be 5. These are 5. Then such sections, here it is 3, in this section also it is 3, and such number of passes are 13. Hope you understand this point. Number of such passes are 13 number. So here tube OD is 44.5. By default we are getting this. What is this tube length per section, which is 21 meters, 21,350 mm. This is the total length of all these tubes. These are 5 tubes going in inverted U type. So what is the total length of all these tubes? 1 plus 2 plus 3 plus 4 plus 5 is 21,000. Because this is a complicated geometry, you have to give this value as input. Based on this value, software calculates gas mass flow rate or gas mass velocity. Now, the outlet temperature we are getting is 457. There are 13 such sections. Suppose we want to make it 12 sections. Give the value 12 and press redesign. Now steam outlet temperature is 447. It is slightly lower than 450 degrees centigrade. That's why you require 13. Here the steam pressure drop is 1.88. You can say it's 2 kg, close to 2 kg, 2 bar. Now this steam pressure will come down if we reduce the number of tubes per section, or if you use number of sections per pass 3. Suppose I make it number of sections per pass as 2. If I press redesign, see the steam pressure drop increasing is almost doubling to 3.9 bar. That is the reason number of sections per pass selected is 3, so that this pressure drop is within the limits. Usually, whatever is the steam pressure, around 7-8% of that steam pressure can be taken as a steam pressure drop inside the superheater. This is a 45 bar pressure boiler, so you can go for up to 3 kg pressure drop in the superheater. Once superheater is over, let's go to economizer section. In this, again, all the sizing details are given in the test boxes. Tube body is 50.8. Water inlet temperature from dereator is 105 degrees centigrade. This is the tube length, which is 1400 mm. Transverse pitch, longitudinal pitch. Then 24 wide by 31 deep. Then you have 2 counter pass and 1 parallel pass. Here this means water is going up and then coming down and again going up. That is 3 pass on water side. On gas side, usually it is single pass. Duct width is nothing but number of tubes wide into transverse pitch. That is the duct width. Duct length is nothing but tube length plus some margin, that is including tube bends. So usually we add 250 to 300 mm here. Suppose you want to customize this design using 44.5 tubes. You can as well give here 44.5 and press redesign. So all these parameters changed based on the new tube. Also you can change the, instead of 1500 mm, 1400 mm, you want to go for 2 meters tube length. Now you have to change duct length to match the tube length. Tube length is 2 meters plus tube bends, which is around 300 mm. So the duct length will be 2300. Now press redesign. This is the revised design. Water outlet temperature coming as 155 degrees centigrade. If you are happy with this, you can continue with this, or you can further modify or optimize this. You can do that as well. If you see in economizer, gas mass velocity is 14,000. Earlier in boiler bank, I told you that gas mass velocity should be around 20,000 plus or minus 10%. That is the optimum design. Here you are getting only 14,000. Means there is scope for optimizing this design further. This also evident from this fact, total draft loss is 13 mm is very low. Usually for economizer section, you can go up to 40 to 50 mm. That is about 2-inch draft loss. So this draft loss will increase only if you reduce the flow area. So that's why uh, reducing the flow area can be done in two ways. One is you can reduce the tube length or you can reduce the tube wide. In this case, let us reduce the tube wide. Say instead of 24, let us go for 16. So 16 into 85 would be the duct width, which is 1360. This is the duct width. Now press redesign to see how this performs. Now the gas mass velocity is 22,000. That's fine, even though it's slightly on higher side, but 22,000 is okay. Now this, if you see the draft loss, it's 31 mm. It's a very pretty good design for as far as economizer is concerned. Water temperature is rising from 105 to 150 degrees centigrade here. And gas outlet temperature is coming to 218. What is the inlet temperature of the gas? If you see the boiler bank, it's upstream of the section. Gas outlet temperature is 353. So 353 is coming down to 218 in economizer section. So this is the heat load, which is again is the heat recovered in the economizer. Then there is heating surface area of 155 degrees centigrade. Gas mass velocity is 22,000. Once the economizer design is over, we can go to next section, which is aerator. In this section, aerator looks like this. Gas is flowing through the tubes. Air is flowing over the tubes. And it's a bare tube air heater. Okay. So air is entering like this. Then it is making a U-turn and entering in the second pass, then again making a U-turn and entering in the third pass, and finally that hot air is out from the other end. This is the general configuration of the air heater. So in this we say 1, 2, 3. 3 pass on air side and single pass on gas side. Usually people prefer staggered pitch on air heaters. That depends upon your requirement. You can as well go for a square or rectangular pitch. So if you see these parameters, on tube side gas is flowing. This gas flow rate is 37,000. And we are sending 100% of the gas through the air heater. So this is the actual mass flow rate. Inlet temperature is 218. See, if you see the economizer section, gas outlet temperature is 218. So gas at 218 is entering air heater. And gas outlet temperature now we are getting is 132 degrees centigrade. Regarding air, air from every fan, it enters 100% of the air is entering this air heater at 26 degrees centigrade. This is the ambient temperature. Based on the temperature at the site, you can modify this value. It can be 20 degrees, it can be 10 degrees as well. So outlet air temperature is 130 degrees in this. So this 130 degrees air now goes to the burner. If you see the air heater configuration details, what we are using is a 63.5 tube, which is 2 meters long. Then pitch is 80 and longitudinal pitch is also 80, 45 wide and 10 deep. And it is a 3 pass, 1, 2, 3. So you can change the passes from 3 to 1, 2, 4, 5, 6, whatever is required. And duct width is 3650. Again, this duct width we are getting from 80 into 45 is the width. And duct length is tube length, 21531. Let's make it a round figure. So let's consider tube length as 2000. Duct length also will be 2000. Press redesign. This is the revised air heater. In case you want to experiment with 50.8 OD tube, you can remove this 63, use 50, and proportionally you can make a transfer switch, lower transfer switch, and also change the length as per your requirement. In this case, let us try with the 50.8 tube. Let's keep tube thickness same, tube length same. Transfer switch can be reduced to 70 because tube body is less, pitch also less, 70. Wide, let us keep 45-10. Let us see how it affects the design. And now duct width would be 45 times 70. That is 3150. Tube length is same. Now press redesign. If you see the performance data here, shell side mass velocity 20,000 is fine, but tube side mass velocity is 49,000 is very, very high. Means on gas side you have very high mass velocity. Usually it should be around 30,000 kg per hour per meter square. So you have to increase the number of tubes, because earlier we were using 63 tube OD. Now we have reduced the tube body to 50. So obviously tube side velocity increases. So to reduce this, we have to increase the number of tubes. Let us increase deep by 20. Let us see. Now tube mass velocity is 24,000 is too low. So you can go for around 16 deep. Now this is fine. Shell side is 20,000, tube side is 30,000. And heat load is 1.1 into 10 power 6 watts. 70 into 45, 70 times 45 is 3150 is the duct width. Tube length is 2 meters. This is a good design. Gas side you have outlet temperature of 123 degrees. What we require is 125 degrees. Air side outlet temperature is 140 degrees centigrade. This is sufficient usually for any burner. This is how we do water tube package boiler design. This is how we customize the design. You can always experiment with different types of tube configurations, different pitches and lengths, and arrive at the proper optimized design. Usually what is the optimum design? You should always aim for the lowest heating surface area. Here it is 689 meters square. Lower heating surface area means less number of tubes, which saves material cost. Once the design is done, you can save the design. Sample 30, save. So the design is saved. If you want to, in future, if you want to open this project, you can just say sample 32 and open this design. This is your design. This is your air heater. This is the economizer, and this is the superheater section. Thank you. Thank you very much for the